Welcome back to AP Chemistry sections 1.3 and 1.4. And in section 1.3, we're going to talk about the elemental composition of pure substances. So let's pull up a diagram so we can see what that looks like. And in this diagram, we can see that we have a solid, liquid, and a gas. And these are all the three different phases of matter. And matter can be broken into two different categories. Over here we have the pure substances, and then over here we have the mixtures. So in section 1.3, we're going to talk about all these pure substances. And then in section 1.4, we're going to talk about these mixtures. And so for right now, we're going to talk about these pure substances. And what a pure substance is it's a chemical that cannot be broken apart anymore and still retain all of its chemical properties. And so you have an element and then you have a compound, and they're both considered a pure substance. And so an example of an element would be something like Ag, or we could have Zn, or we can have Au, or we can have oxygen, but it has to be oxygen like this. And so you can basically think of the periodic table of elements when you have this element right here. And what makes all these elements is the fact that they all have one specific type of atom. They're all made up of the same type of atom. So we're going to say this is only one atom, and that's what an element is. And then for a compound is going to be at least two or more different atoms bonded together. So I'll put that we have two or more different atoms. And the key word there is that these are going to be different. So an example of a compound would be something like we had H2O. We have two hydrogen atoms and then one oxygen. We did something like C2H3. We could have something like C4H6. And these are all compounds. And not only are these all compounds, but they're also all going to be molecules. And a molecule is going to be more than one atom bonded together. And so we could have something like this. We could have something like O2. O2 is also going to be a molecule, but it's not considered a compound. And so all of these right in here, these are all going to be molecules. So I'll put molecules right here. And so it's important to know that all these compounds, these are molecules, but not all molecules are compounds. And so let's write that down. We can say that we have that all compounds are molecules, but not all molecules are compounds. And so there's basically going to be two different categories of these molecules. So we can say that in molecules, there's two types. And those two types are going to be, the first one is going to be an empirical. Molecules can become empirical, or they can also be molecular. So we'll put empirical, and then we'll put molecular. And what an empirical is, it's going to be the smallest ratio of all the atoms that are in that formula, that chemical formula. So I'm going to say this is going to be the smallest ratio. So we'll say it's the smallest ratio of all the atoms in that chemical formula. And what a molecular is going to be what the chemical actually looks like. So this is going to be what the chemical looks like. And so let's try a problem where we can see these empirical and molecular chemicals. So here is the problem. And what we have here is we have a molecular formula, and here are all molecular formulas, which means this is what each of the chemicals actually looks like. So if you were to go and study these chemicals, this would be the exact ratio of each of the atoms. And so over here, what we want to do is you want to write out the empirical formula for these molecular formulas. And the empirical formula is the same thing as saying the formula unit. And so if you have N2O4, if you were to reduce this molecular formula, what you would get would be NO2. NO2. Because I just divide each of these by a 2 and we get NO2. And so we could have something like the molecular formula of C6H6, and the smallest ratio of this would be would be that we have CH, because we could divide each of these by a 6. And for this molecular formula, this is H2O, which is water, and this is already the smallest ratio. So not only is this going to be a molecular formula, but it's also going to be the empirical formula. So we can put H2O over here. For this one, we have H2O2, that's the molecular formula, and then to reduce this, the smallest version of this would be HO. And so we have the molecular formulas over here and the empirical formulas over here. And a special note that if you look at this one right here, we have H2O. This is the molecular formula. It's also going to be the empirical formula. So sometimes they can be the exact same. And so now let's try practice question number 1, where we have to determine if a chemical is going to be either empirical or molecular. In practice question number 1, it wants us to determine if the following compounds are molecular or empirical. And if the molecule is molecular, write the empirical formula. So for this first one, we have C4H8, and that can be reduced. We can divide each of these by a 4, and we would get CH2. And so this would then be a molecular. This one right here, the C4H8, would have to be molecular because it's definitely not empirical, because we can be reduced. And so this right here would be a molecular formula, and this would be the empirical formula of that molecular formula right here. And so now let's try CH4. And so this one cannot be reduced anymore, so it must be empirical. So you can put this one is going to be empirical. But we don't really know if this is going to be molecular or not. We would have to get some more information. And so this one right here, we got C3 and 12. That one is going to be a molecular formula because this can be reduced. So this can be reduced to CN4. And so that's going to be reduced. So therefore, this one must be a molecular because this right here is going to be the empirical. And so for this last one, we have C2H5, and that one cannot be reduced anymore. So this must be empirical. It's empirical. But the thing is, with this one here and this one here, these could both be molecular, just like water over here is molecular. We would need some more information to figure that out. And so what you would need to know, the molar mass of the molecular formula to determine if this is in fact going to be an empirical or molecular, because it could be that this right here is not molecular and it's already been reduced. So you would need the molar mass of the molecular to figure that out. So let's see how we would take something like C2H5 and given the molar mass of the molecular, determine what kind of class it would go in, if it's going to be empirical or molecular. So let's go ahead and take that same C2H5, and we just said this is going to be an empirical formula. So I want to write empirical up here, and let's say that we know what the molecular formula is of this, and let's say that's going to be something like C4H10, and this is going to be a molecular, which means this is going to be what the chemical would actually end up looking like. And you'll notice to go from the empirical to the molecular, that's going to be increased by a factor of 2. And so if we compare the molar mass of each of these, you'll see that the molar mass of the empirical is going to be 29, and the molar mass of the molecular is going to be 58. And so if you look at the empirical molar mass and the molecular molar mass, that's going to be increased by that same factor of 2. And so what we can do is we can make 2 different equations that relate all this information together. And those 2 equations are going to be this. The first one's going to be that if you have a molecular molar mass, that's going to be equal to some n value, in this case it's going to be 2, and times the empirical molar mass. The empirical molar mass. And we do the same thing for the formula. We can say that we have the molecular formula, the molecular formula, and that's going to be equal to some n value, which will be the same n values up here, and times the empirical empirical formula. And so what we could do is we can take this information to solve questions. So let's go ahead and try practice question number 2. And in practice question number 2, it wants us to determine the molecular formula of a compound with an empirical formula of NH2 and a formula mass of 32 AMUs. So when you read this question, you need to know that if you're given an empirical formula, you're also given the empirical molar mass. Because if we can take this right here, this NH2, and I can tell you what the empirical molar mass is just by finding the molar mass of this right here. And so when you find the molar mass of this, you're going to get 16 grams per mole, or atomic mass units. That means the same thing. And so if you have the empirical molar mass and you know the molecular molar mass, you can find how much it increases by. You can find that this n value, this factor of n. And so what we can do is we can do this equation right here. And so what we'll do here is just say the molecular molar mass is going to be 32. So I'm going to say that I've got 32 here. And that's going to equal some value n, some multiple. And then we'll take the empirical molar mass, which we found over here was 16. So we'll do this n times 16. And then we'll solve this for n, and we get that n is going to equal 2. And so now that we know what n is, we can go ahead and use this equation over here. And we can say, well, we know what the empirical formula is, and we're going to find what the molecular formula is. So we can say that the molecular formula is going to be equal to, and well, the n is going to be this 2 value, so I'll put a 2 here, and then we want to multiply by the empirical formula, which is going to be right here, this NH2. So we're going to say NH2 down here. And so when we do this, all we have to do is take the empirical formula and multiply the ratios of each of the atoms by 2. So you'll get N2H4, and this would be the molecular formula. And so you can see here that the N right here just comes right in there once we find that. So to find the molecular formula in practice question 2, we really needed 2 things. And the first thing that we had to have was we had to have the empirical formula. We need the empirical formula. And they gave it to us right here. It's NH2. And the other thing that we had to have was we had to have the molar mass of the molecular formula, which is right here. So we need the molar mass of the molecular formula. And so one way that we can find the empirical formula is through a process called elemental analysis. And elemental analysis is basically going to be a technique used to find the percent composition or the ratio of each atom in a chemical formula. And by finding the percent composition, we can find the empirical formula. And so there are some rules that you want to follow if you're given a percent composition to find the empirical formula. So let's go ahead and take a look at what some of those rules look like. So let's go over some of the rules for finding an empirical formula from a percentage. And remember, we find a percentage through a process called elemental analysis. And so we could be given something like this. So let's say that you do an elemental analysis and you find that you're going to have 89% oxygen and then you have 11% hydrogen. And this is all going to be in one sample. And what you want to do is you want to find the chemical formula that has 89% oxygen and 11% hydrogen. So to figure this out, you want to follow some rules or some steps to figure out the chemical formula for this. And so the first rule or the first step is to assume that you have 100 grams in this sample right here. And if we assume that we have 100 grams of oxygen and of hydrogen, and 89% of that is going to be oxygen, that means that we'll have 89 grams of oxygen. And so you want to do this if you're given a percentage. So I'll put if we're given a percentage. And if you're not given a percentage, then you'll probably be given grams, and you can just use the grams and skip this step right here. So the next step would be to divide. You're going to divide the percentage, which would be these percents right here, and they would be now in grams. If you assume that you have a 100-gram sample, you're going to divide the percent, and I'll put or grams, because you may be given grams instead, or grams by the molar mass, by the molar mass. And what this does is this will convert to a mole, because a mole is going to be a gram divided by the molar mass. So you're going to take these percentages and divide them by the molar mass of each atom, and that will give you the moles of oxygen, and it'll give you the moles of hydrogen in this sample. So after step 2, what you did was you found the mole ratio of each atom that's in that chemical compound. So you found the mole ratio of oxygen and the mole ratio of hydrogen. And so what you want to do in step 3 is you want to divide by the smallest mole ratio. So you want to divide by the smallest mole ratio. And what that will do is that will get this the smallest number to be a 1, because the goal for this would be to get all whole numbers for each of the atoms that are within that chemical compound. So after step 3, the goal is to get whole numbers for all your mole ratios, but you may not be given whole numbers. So I'm going to put down here that if you get some number x and then you get 0.5 and you want to get a whole number, you're going to multiply all of the mole ratios by 2, and that will get rid of that 0.5. But you may not be given a some value 0.5. It might be something like a 0.3. So I'm going to put down here that if you get some value x and it's a 0.3 for one of the mole ratios, you're going to multiply all mole ratios by a 3. And if you do that, the 0.3 will go away. And now whenever you round, you only want to go up or down by 0.1. So I'm going to put only go up or down by 0.1. You don't want to go any more than that, because these numbers are very specific for this mole ratio. And so like if you get like 0.5, you don't want to round that all the way up to the next whole number. What you want to do is you want to multiply by 2. So let's try to do practice question number 3, and we can use information to solve that problem. And practice question 3 says this. It wants us to determine the empirical formula of a compound that contains 73.9% mercury and 26.1% chlorine by mass. And so what I like to do for these types of questions is I like to put the mercury over here, and I'll put the Cl over here. And each atom that I have that's within that compound, I like to make it its own column. And so I'll do all the mercuries here, and I'll do all the Cl's over here. And so what I'm going to do is say, okay, I got 73.9% mercury. The first rule right here, rule number 1, it tells me to assume 100 grams sample. And that means if I assume 100 gram sample, this right here would be 73.9 grams of mercury, and the Cl, that's got 26.1%, that's going to be 26.1 grams. So these are both going to be now in grams. And so the rule number 2, it wants me to divide by the molar mass, and that will convert this to moles. So I'm going to divide each of these by the molar mass, and the molar mass of Hg, if you go and look at a periodic table, that's going to be 200 grams per mole, and the molar mass of Cl, that's going to be 35 grams per mole. So those are the two numbers that I'm going to divide by. And so I'm going to have 200 here, and I'll have 35 here. And so now what I do is when I divide these two, I'm going to get 0.3695 for the mercury, and the Cl, I'm going to get 0.745. And the next step I'm going to do, this third step, is to divide by the smallest mole ratio. Well, that's going to be this one right here. It's going to be the mercury. So I'm going to divide each of these by this 0.3695, and this gets me to a 1. So now I have a 1 right here. And when I do to one of the mole ratios, I have to do to the other mole ratio. So I'm going to divide this by 0.3695 as well. And when I do that, I'm going to get 2.01. And so now that I got a 1 for the mercury, I got 2.01 for the Cl, and this one right here, I can round that just as a 2, and I don't have to worry about this because my rule over here, it says go up or down by only this 0.1, so I can basically just ignore this right here. And so what I'm going to do is, my chemical formula is going to be Hg, and I have one of those, and then I have Cl right here, and I got two of those, so I'm going to do Cl, and I'll put a 2. And then this would be the empirical formula. And so let's try example question number 1. In example question 1, it wants us to determine the empirical formula for an oxide of gold that is 10.8% oxygen by mass. So to do example question 1, you need to know that oxide of gold is going to be a chemical compound that only has 2 atoms. One's going to be oxygen, and then one's going to be gold. And you know that the oxygen is going to be 10.8%. So see if you can figure out the answer to this question. To answer example question 1, you need to know the percent of oxygen and the percent of gold that's within this chemical compound. So if you have 100% of oxygen and of gold, and we subtract the percent of the oxygen, we can get the percent of gold, which is going to be 89.2%. And so what we'll do now is we'll make 2 different columns, one for the gold and then one for the oxygen. And if we have 89.2% of the gold, I'm going to put that number here. And if we assume that we have a 100-gram sample, then we have 89.2 grams of the gold. And so for the oxygen, we have 10.8%. And if we have 100 grams, that's going to be 10.8 grams of the oxygen. And so if we take the grams and we divide by the molar mass, we can get number of moles. And so the molar mass of Au, or gold, is going to be 197. And then the molar mass of oxygen is going to be 16. And so when we divide these, we're going to get 0.45 for the gold, and then we'll get 0.675 for the oxygen. 0.45 is smaller, so we're going to divide each of those by 0.45. And then this number right here is going to be a 1, and the number over here is going to be 1.5. So these are the mole ratios, and we still need to get whole numbers. This is a 1, that's a 1.5. And so what we'll do is we'll multiply both of these numbers by a 2. And then we're going to get a 2 here, and then we'll get a 3 here. So these two numbers, the 2 and the 3, are going to be the number of atoms that's within this empirical formula. So we're going to have Au2, oxygen 3. And so now let's try to do example question number 2. In example question 2, it says, what is the empirical formula of a compound that contains 29.84 grams of sodium, 67.49 grams of chromium, and 72.67 grams of oxygen? So take some time to think about what you think the answer would be. So to answer this question and find the empirical formula, and you have 3 different atoms that are part of this chemical formula, what I like to do is I like to make different columns of each of the different atoms. So I'm going to put that I got sodium, I have chromium, and then I have oxygen. And what I'm going to do is I'm going to put the amount in grams for each of these under these different columns. So for the Na, I've got 29.84 grams. For the chromium, I've got 67.49 grams. And then for the oxygen, I have 72.67 grams. And what I'm going to do with these grams is I'm going to divide them by the molar mass, because grams divided by molar mass will be moles, and that'll tell me the mole ratio of Na to Cr to oxygen that I have in this empirical formula. So I'm going to take this and divide it by the molar mass of Na, which is going to be 23. The molar mass of Cr is going to be 52. And then the molar mass of oxygen is going to be 16. And so when I divide all these, I'm going to get 1.3 for the Na, I'll get 1.3 for the Cr, and then I'll get 4.5 for the oxygen. And so now that I did this, I'm going to divide by the smallest number, which is going to be the 1.3. So all of these get divided by 1.3. And that will make this one and this one both have a 1. So I'm going to have a 1 there, a 1 there, and then I'll get a 3.5 here. And so I want to keep all these numbers, the ratios the same, and I want to get rid of this 0.5 right here. So I'm going to have to multiply all of these right here by a 2. So I'm going to get a 2, and then this would be 7. So the empirical formula is going to be Na2Cr2O7, and this would be the empirical formula. So now what I want to do is go back to something that we said previously. And what we said was that if we wanted to find the molecular formula, we needed two things. And the first thing that we had to have was we had to have the empirical formula. And the other thing that we had to have was we had to have the molar mass of the molecular formula. And what we said was that if we wanted to find the empirical formula, we needed to have either the percentage or the number of grams or moles of each of the atoms in the compound. And now, one way that we could find the number of moles of each of the atoms in a compound what we're going to do is we're going to use a technique called empirical analysis, which is basically going to be a reaction that we're going to use to find the number of moles or atoms in the compound, and then from there we can figure out what the empirical formula is. Now, we were able to find the molecular formula in practice question number 2, and we were able to find the empirical formula in practice question number 3 and example question number 1 and 2. And so now what we'll do is we're going to find the number of moles of each of the atoms in a compound through this reaction. So let's take a look at that. So let's take a look at a reaction where we got carbon and it's going to combine with oxygen, O2, and that's going to make CO2 or carbon dioxide. And let's say that we have 132 grams of carbon dioxide, and what we want to do is we want to figure out how many moles of carbon do we have on this side. Well, if you have 132 grams of carbon dioxide, what we can do is we can go from grams to moles using the equation that a mole is going to be a gram divided by the molar mass. And so what we'll do here is we'll do 132 and we'll divide by the molar mass of CO2, which is going to be 44, and that's going to be 3 moles of CO2. Well, now that we have 3 moles of CO2, what we'll do is we'll figure out how many moles of carbon that is. So if we have 3 moles of CO2, what we'll do here is we'll figure out how many moles of atoms of carbon that is. So for every 1 molecule of CO2, that's going to be 1 carbon atom. And then we're going to have molecules here and molecules here canceled out. And so we'll get 3 moles of atoms of carbon. And so if you look at the chemical reaction that we have, you can see that we have a carbon here and we have 1 carbon here. So the carbon here and the carbon here, it doesn't go anywhere else as a product. The carbon here is a reactant and the carbon here is a product, and it only goes from this reactant here to this product over here. So the moles of carbon that we got here is going to be the same number of moles of carbon that we'll get over here. So let's see how we can use this information to solve a problem. So a typical elemental analysis problem might look something like this. And in this setup, we have a sample right here, and in this sample, it's going to be a hydrocarbon, which means it will have some type of carbon ratio to a hydrogen ratio. And the goal for this experiment is to figure out the ratio of carbon to hydrogen, the empirical formula of that. And so what we're going to do is we're going to combine this hydrocarbon with oxygen, and we're going to burn it. And when this hydrocarbon combines with oxygen, it's going to go through a combustion reaction. And a combustion reaction is always going to produce CO2, and it's also going to produce H2O. And so what we have here is, as this sample right here gets combusted with this flame, what happens is it's going to go through this tube right here, and right in here we have water absorbed. So all the water that's going to be produced from the reaction will be absorbed in here. And then the rest of it, the CO2, will keep on going down over here. And the CO2 will be absorbed in this chamber over here. And then the unused oxygen will end up leaving. And so what we'll do is we'll measure the change in mass of each of these chambers. And the change in this chamber would be the amount of water that's going to be produced. And then the change in this chamber over here will be the amount of CO2 that's going to be produced. And if you look at this reaction, you'll notice that we have an H here, and we have another H all the way over here. And so we also have a carbon here, and we have a carbon over here. So the number of moles or grams of carbon right here is going to be the number of moles or grams of carbon over here. And once we know the moles of each of these, carbon and hydrogen, we can find the empirical formula of this. So let's use this information to do practice question number 4. So practice question 4 says an empirical analysis of a hydrocarbon was combusted to produce 88 grams of CO2 and 48 grams of H2O. Determine the empirical formula of the hydrocarbon. And so what you want to do for this is you want to figure out the number of moles of carbon and the number of moles of hydrogen. And if you know the moles of each of these, then we can find the empirical formula of this compound. And so what I'm going to do is say that I've got 88 grams of the CO2, and then I have 48 grams of this H2O. And I'm going to figure out how many moles of carbon I have in 88 grams of CO2, and I'll figure out how many moles of hydrogen I have in 48 grams of H2O. And so what I'll do first is I'm going to convert the grams of CO2 to moles of CO2, and the molar mass of CO2 is going to be 44. And so if I do 88 divided by 44, I'm going to get 2. So this will be 2 moles of CO2. And then I'm going to take this, and I'm going to say that for every 1 CO2, that's going to have 1 carbon atom. And so what will happen here is I'll get 2 moles of carbon. So I know that I got 2 moles of carbon over here, which means I'm going to have 2 moles of carbon over here. And for this one, it says that I have 48 grams of H2O, and the molar mass of H2O is going to be 18. And so when I do 48 over 18, I'm going to get 2.66. So I'm going to have 2.66 moles of H2O. And for every 1 H2O, I'm going to have 2 hydrogen atoms, which means I'm going to have 5.32 moles of H atoms. And now that I know how many moles of H I have on this side, that's the same number of moles of H I'm going to have on this side. So I'm going to put the carbons here, and I'll put the H here, and I'm going to say that I got 2 moles of carbon, and I have 5.32 moles of H, and the smaller of these two numbers is going to be the 2, so I'll divide each of these by 2, and I'm going to get a 1 here, and then I'll get a 2.66 here, and these are going to be the mole ratios of carbon to hydrogen, but I got to get whole numbers, so I'm going to multiply both of these by a 3, and so I'm going to get a 3 here, and then I'll get an 8 here, and so the empirical formula for this hydrocarbon is going to be C3H8, and this is going to be the answer. Now let's try example question number 3. In example question 3, it says a student takes a 2.5 gram sample of an unknown hydrate copper 2 sulfate, which is CuSO4, and then it's got this unknown H2O attached to it, and heats it until all the H2O is driven off. If the mass of the anhydrase CuSO4 is 1.6 grams, what is the value of X in the hydrate sample? So see if you can figure out the answer to this question. Now in example question 3, the first thing I'm going to do is I'm going to take this 2.5 gram sample of the hydrate copper 2 sulfate and I'm going to put it under here for the reaction so I know where it goes. And then what I'm going to do is I'm going to take this 1.6 grams of the copper 2 sulfate, I'm going to put it right here. And then what I'm going to do is, because I don't know the amount of H2O that was driven off, I'm going to put a question mark and then a grams right here. And this just helps me keep everything in order. And one thing you need to know is that the total grams on the product side is going to be equal to the total grams on the reactant side. And so this means that these two right here have to add up to equal this right here. And so if we do 2.5 minus 1.6, we'll get 0.9. And this 0.9 is going to be the 0.9 of the H2O over here. And so if we want to get the number of moles of this H2O, we'll do 0.9 divided by the molar mass of H2O, which is going to be 18. And we're going to get 0.05, and that's going to be moles of H2O. And so what we have here now is we have the moles of H2O, and we need to get the moles of the CuSO4. So what we can do is just do 1.6 grams of the CuSO4, and we'll divide it by the molar mass, which is going to be 160, and then we're going to get 0.01, and that will be moles of CuSO4. And so now that we have moles of CuSO4 and we have moles of the H2O, what we can do now is we can set up something like an empirical analysis where we had the CuSO4, we have moles of that one, and we have the moles of the H2O. And what we'll do here is say that we got 0.01 here, and then we have 0.05 here. And so when we did the empirical analysis, the next step after we got the moles was we divided by the smallest number. And the smallest number between 0.01 and 0.05 is going to be this 0.01. So I'm going to divide each of these by 0.01, and I'll get a 1 here, and then I'll get a 5 here. And so for this chemical right here, it means that for every 1 CuSO4, I'm going to have 5 H2O. And so this would be the answer. Now let's bring back the idea of how to find an empirical formula. And what we said was, if we wanted to find the empirical formula, we need to either have the percentage or the amount in grams / the moles of each atom in the compound. But what if we wanted to find the percentage of each atom in an empirical formula? Well, we would need to have the empirical formula. So if you want to find the empirical formula, you need to have the percent or the grams or the moles of each atom in that chemical compound. So this is what you need to have in order to find this right here. But if you want to find the percentage of each atom, you need to have the empirical formula. So doing this is like doing this in reverse. And so what we'll do now is we'll take a look at how we can find the percentage if we're given an empirical formula. So let's say that we have an empirical formula, something like NaCl, and what we want to do is we want to find the percent by mass of the Na or the Cl. And there are two different equations that we can use to solve that. And the first one is that the percentage of some x value, and the x can represent the Na or the Cl, is going to be equal to the molar mass of the X value divided by the total molar mass, and I'll put a T right here to represent total. And we'll take that fraction and then multiply it by 100, and that will be the percent. The other equation that you can do is that the percentage of some X value will be equal to the amount in grams of X divided by the total amount in grams, and we'll take that fraction and then multiply it by 100. And what we want to do is find the percentage by mass of Na or Cl. So we can't do this one because we need grams. So we're going to have to use this one, the molar mass. And if we go to the periodic table, the molar mass of Na is going to be equal to 23. So we'll put the Na is going to be 23. And then the molar mass of the Cl is going to be 35. And what we'll do here is say that the percentage of Na by mass is going to be equal to, I need the molar mass of the Na, which would be 23, so we'll do 23 up top, and then we'll divide that by the total molar mass of the Na and Cl, which is going to be 58, and so I'll put 58 here, and we'll take that fraction and multiply it by 100, and then we get the percentage of Na would be equal to 39.6%, and so this would be the percentage of Na by mass for NaCl. Now, to find the percent of the Cl, what we could do is we could do this equation right here, but if we know that the Na is going to be 39.6 and there's only two different atoms as part of this compound, then we can just say that 100% minus the 39.6%, well, that's going to be equal to 60.4%. So this will be the mass percent of the Cl in this compound. So now let's try to do practice question number 5 using this information. Now, practice question 5 says to find the percent composition of K in KCl, and then the other part says to find the percent composition of K in KCl given 10 grams of KCl. So for this first part, we don't have the amount in grams, so we can't do this equation right here. We have to do this equation right here where we have to use the molar mass. So I'm going to go to the periodic table and I'm going to look up the molar mass of K and of KCl. So the molar mass of K is going to be 39, and then the molar mass of KCl is going to be 74. So I'm going to use these in this equation right here to find the percent composition of K. So the percent composition of K is going to be the percent of K would be equal to the molar mass of K, which is going to be this 39 right here. So we'll do 39, and then we'll divide that by the molar mass of KCl, which is going to be 74, and then we'll multiply that by this 100 right here, and that's going to be 53%. So for this next part, I'm going to find the percent composition of K in KCl given 10 grams of KCl. So to solve this, I can do this equation right here if I want to, but because we already did that in this first part, let's do this equation right here instead. And for this equation, we need to get the grams of just K. And so what I'm going to do is I'm going to convert grams of KCl to moles of KCl. And to do that, I'm going to say that a mole is equal to the amount in grams divided by the molar mass. And so I'm going to take 10 grams right here of KCl, and I'm going to divide that by the molar mass of KCl, which is 74 up here. So I'll do 10 divided by 74, and that's going to be 0.135, and that'll be moles of KCl. So I'm going to say 0.135 moles of KCl. I'm going to convert this to moles of just K, and so I'm going to put, for every 1 KCl that I have 1 K atom, and so I'm going to have 0.135 times 1 divided by 1, and that's going to be 0.135, and that'll be moles of K. So now that I have moles of K, I need to go to grams of K, so I'm going to take the moles and multiply it by the molar mass, and that'll give me grams. So I'll take the 0.135, and I'm going to multiply the moles by the molar mass, which is right here, 39. So I'm going to do 0.135 times 39, and that will be 5.27, and this will be the grams of K. So now I have the grams of K, and I have the total grams in the compound, in the chemical compound. So I'm going to have 5.27 divided by 10, which is the total, times 100, because that's this part right here, and that'll be equal to 53%. So notice that we got 53% here, and we got 53% here. We got the same percentage, and we did this question two different ways. So now let's try to do practice question number 6. So practice question 6 says to find the percent composition of Ca and Cl in CaCl2. So because this question doesn't give me grams, I can't do this equation right here. And I'm going to have to do this equation right here. And this equation gives me a molar mass. So the first thing I'm going to do is I'm going to look up the molar mass of Ca and Cl. So if I go to the periodic table, the molar mass of Ca is going to be 40. And the molar mass of Cl is going to be 35. And so what I'm going to do now is say the percent of Cl is going to be equal to the molar mass of Cl in this compound, and I have 2 Cl's, so I'm going to put a 2 times the mass of just 1 Cl, which is 35 up top, and then I'm going to divide that by the total molar mass of this compound right here, which is going to be 2 times 35, and then I have just 1 Ca, and 1 Ca is 40, so that's going to be 110, and I'll take that and multiply it by 100, because there's a 100 right here in the equation, and that's going to be equal to 64%. And so now what I can do is I can find the percent of Ca, and to do that, I already know the percent of the Cl, and 100% minus the 64% is going to equal the percent of the Ca, and that's going to be 36%. So here are the two different percentages of the answer. So now let's go to section 1.4 and talk about the composition of mixtures. So we just finished talking about section 1.3 with the pure substances, and now we're going to move on to section 1.4 and talk about mixtures. And mixtures can be broken up into two categories. We have the homogeneous mixtures and the heterogeneous mixtures. And we're going to talk more about these in section 3.7. But for right now, we're just going to talk about what a mixture is. And a mixture is going to be a combination of two or more pure substances. And so if we take something like H2O, which is a pure substance, and we take something like NH3, which is also a pure substance, and we mix those two together, that will be considered a mixture. And so the way that we're going to quantify a type of mixture is with a couple of different equations. And the first equation that you have to know is a mole fraction. And a mole fraction, sometimes you might see that as just a regular X like this. That's going to be equal to the number of moles in the mixture that we're interested in. So I'll put moles of A here, divided by the total number of moles in the mixture. So I'll put total moles. And one thing you have to know about this is that these are not grams. These are moles. A mole fraction, they have to be in moles for this. And you might notice that this fraction right here, if we have moles of A divided by the total, well, that's just going to be a decimal. And if we take that decimal and we multiply it by 100, we're going to get a percentage. So if we take the mole fraction and we multiply it by 100, we're going to get the percent in that mixture. So we'll get the percent of whatever mixture is in there. And if we take all of these mole fractions and we add all of them up, we're going to get 1. So if we sum all of the mole fractions up, we get 1. We could also say that if we take all of the percentages for each different component in the mixture and we add all the percentages up, we'll get 100%. So let's see how we can use these equations. So what I'm going to do here is I'm going to make this container, and in the side of this container, I'm going to put a couple of pure substances. So let's say I'm going to put 1, 2, 3, 4 circles right here, and each of these circles represents 1 mole of any particular pure substance. And now I'm going to take another pure substance like this blue, and I'll do 1, 2, 3, 4, and we'll do like 5. So these are now 5 moles of a different pure substance. And let's say I want to get the mole fraction of the pink and of the blue. Well, if I want to get the mole fraction of this pink, what I'm going to do is I'm going to count up how many moles that I have in here. So I have 1, 2, 3, 4. So I have 4 moles, and I'm going to divide that by the total number of moles that I have in here, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'll do 4 divided by 9, and that would be 0.44 repeating. So this would be the mole fraction of the pink in here. And if I want to get a percentage, I'm just going to do 0.44 times 100, which would be 44%. And this will be the percent of the pink that I have in here. And now for the blue. If I have 1, 2, 3, 4, 5 blues, I have 5 blues divided by the total, which would be 9. That's going to equal 0.55 repeating. And so this would be the mole fraction of the blue. And if I want to get a percentage, I'll just take this 0.55, multiply by 100, and I'll get 55%. So notice if I take the 0.44 and the 0.55 and add those up, I get 1. So now let's use this information to do practice question number 7. So practice question 7 says a student mixes 51 grams of NH3 and 36 grams of H2O. Determine the mole fraction and percentage of each chemical. And so we have NH3 and H2O, both pure substances, and when we mix those two together, we're going to find the mole fraction of each of them. And so we can use these equations down here. And so what we'll do here is take 51 grams, and I have to convert that to moles because this right here is in moles. And so what I'll do here is do 51 divided by the molar mass of NH3, which is going to be 17, and that's going to be equal to 3 moles of NH3. And now what I'm going to do is I'm going to take 36 grams of H2O and convert that to moles. So I'm going to have 36 here divided by the molar mass of H2O, which is going to be 18, and that's going to be 2 moles of H2O. And so what I'll do now is I'm going to take the 3 moles of the NH3 divided by the total moles, which is going to be 3, and 2, which is going to be 5. So I'm going to do 3 divided by 5, and that's going to be 0.6. So the mole fraction of NH3 will be 0.6. And if you want to get a percentage of the NH3 that's within this mixture, you would do 0.6 times 100, and you would get 60%. And I'll do the same thing over here for the H2O. I have 2 moles of H2O divided by the total, which would be 5. And when I do 2 divided by 5, I'm going to get 0.4. And then this would be the mole fraction of H2O that's in this mixture. And to get the percent, you do 0.4 times 100, so you're going to have 40%. So now let's take a look at how we can find the percent by mass for mixtures. So we already talked about how we can find the percentage by mass of something like a single molecule. And we said there were 2 ways that we could do this. We could either use the amount in grams, or we could use the molar mass. And we did this in practice question number 5. And what we did in practice question 5 was we found the percentage of K in KCl. Now for mixtures, we're going to do something very similar, but we're going to find the amount of something like KCl in a mixture that has KCl with something like NaCl, or we can find the amount of K in a mixture that has KCl and NaCl, or we can find the amount of Cl in a mixture that has KCl with NaCl. So we can have lots of different combinations, and we can also use this mixture concept to find an amount of AU that's combined with AU and Cu. And for both of these cases, for all these cases for mixtures, you're going to either use grams or a molar mass. And the equation that you use for this is the same one up here. And that equation is going to be that the percentage is going to be equal to some amount that we're interested in divided by the total times 100. And so let's do a practice question 8 so we can see how we can use this information. So in practice question 8, it says a student has a 20-gram mixture of zinc and nickel. To determine the percent composition of zinc, the student reacts a sample of the mixture with copper 2 chloride to produce ZnCl2 and Cu as shown below. If 13.6 grams of ZnCl2 was recovered, what is the percent by mass of Zn in the mixture? And so what we have here is a student's got this zinc and nickel mixture, and they're going to react this mixture with this CuCl2 right here, and that's going to make this ZnCl2. And so if we know the amount of Zn that's in this ZnCl2, that's going to be the same amount of zinc that's going to be over here. And this zinc is what's going to be part of this zinc that's part of that mixture. And so if we know the amount of grams of zinc that's right in here, and we know the total right in here, that we can use this equation and we can take the amount that we're interested in divided by the total times 100, and that'll give us the percentage. And so the question says that we have 13.6 grams of this ZnCl2. And so the first thing I'm going to do is I'm going to convert this grams to moles by dividing by the molar mass, which is going to be 136. And that's going to be equal to 0.1 moles of ZnCl2. And so now what I'm going to do is I'm going to convert this from moles of this ZnCl2 to moles of just the Zn. And so for every 1 ZnCl2, that's going to be 1 Zn. And so I'm going to have 0.1 times 1 divided by 1, and that's going to be 0.1 moles of Zn. And now that I have this 0.1 moles of Zn, I need to go to grams. And to go from a mole to a gram, I'm going to do this equation that a mole is equal to the amount in grams divided by the molar mass. And the molar mass of Zn is going to be 65. So I'm going to take 0.1 times 65 to get the amount in grams. So that's going to be 6.5 grams of Zn. And now that I know the amount of Zn that I have as part of that mixture, and I do 6.5 divided by the total, which is this right here, is 20, and I multiply that by 100, I'm going to get 32.5%. So this would be the answer. Now let's try example question 4. In example question 4, it says if an unequal mixture of LiBr and KBr contains 70% Br by mass, which compound in the mixture has a higher amount by mass? And so I'm going to make a picture for what's going on in this question. And it says that we have LiBr, and we also are going to have KBr. And these amounts are going to be unequal. And the question tells us that we have 70% by mass of Br. And so if we have 70% Br in this mixture, which of these compounds, either the LiBr or the KBr, has the higher amount in grams? So take some time to think about what you think the answer would be. So to solve example question 4, what I'm going to do is I'm going to figure out what is the maximum amount of Br that I can have in LiBr. And to do that, I'm going to do 80 for the molar mass of Br divided by the molar mass of LiBr, which is going to be 87, and I'll multiply that by 100, and then I'm going to get 92%. And this would be the percentage of Br if I have nothing but LiBr. And I'm going to do the same thing over here, but I'm going to do it for KBr. And so for KBr, I'm going to have 80 for the molar mass of Br divided by the molar mass of KBr, which would be 119, and then I'll multiply that by 100, and I'm going to get 67%. And so this would be the percentage of Br if I have nothing but KBr. And what I'll do now is I'm going to put this on a percentage line where over here on this end, I'm going to represent the Li Br, which would be the 92% Br. And over here, I'm going to have the KBr, and this would be the 67% Br. And so if I have 70% Br, that means I'm going to have a range somewhere in here in the middle. I don't have all KBr, I don't have all LIBr, and so I need to find the halfway between these two. And to do that, I'm going to do 92 plus 67, and I'm going to divide that by 2. And this will be the percentage that's going to be exactly at half the point. And so that's going to be 79.5%. And so that would be the number right in here. This would be 79.5%. And because 70 is going to fall on this end, it means that I'm going to have more KBr in the sample than LIBr. So the answer is going to be this one right here, the KBr. Now let's do example question 5. So this question has 2 parts, and in the first part, we're going to figure out how many grams of KCl are in the supplement, and then the next part, we're going to figure out the molar mass of the entire supplement. And for both of these parts, we're going to use the same equation, and that equation is that the percentage is going to be equal to the amount divided by the total times 100. So for this first part, we're going to find how many grams of KCl are in the supplement, and we're going to take this equation right here and say the percentage of K is going to be 22%. So I'm going to put down 22%, and that's going to be equal to the amount of potassium that we have in the sample, and we don't know what that amount is. So I'm going to put a G here for grams, and then we're going to divide by the total amount of the supplement, which is going to be this 0.45 grams. So I'm going to put 0.45 here. And then what I'm going to do is multiply this by 100, and I'll solve this for G. And when I solve this for G, which would be the grams of potassium that's in the supplement, I'm going to get that's equal to 0.099, and that's going to be grams of this K right here. And so what I'll do now is say this is the grams of potassium in the supplement. I'm going to convert this from grams to moles. So to convert from grams to moles, I'm going to use this equation that a mole is equal to the amount of grams divided by the molar mass. So I'm going to take 0.099 and divide it by the molar mass of K, which is going to be 39, and I get that from the periodic table, and that's going to be equal to 0.00253, and that's going to be moles of K, or potassium. And now what I'm going to do is I'm going to convert from moles of just potassium to moles of KCl. And so I'm going to say for every 0.00253 moles of K, that's going to be over 1. And I'm going to convert from moles of this to moles of KCl. So for every 1 potassium, there is 1 KCl. And so that means I'm going to have this number here times 1 divided by 1. And so I'm going to say that I've now got 0.00253, and that's going to be moles of KCl. And so now that I know how many moles of KCl that's in this supplement, I'm going to go from moles to grams, and I'm still going to use that equation right there. And so what I have to do is I'm going to take the number of moles and multiply it by the molar mass. And the molar mass of KCl is this right here. So that's going to be 0.00253 times the molar mass is 74.55. And when I do that, I'll get 0.188 grams, and that's going to be of KCl. So this will be the answer for the first part. Now we'll figure out the next part. And for this next part, we're going to figure out the molar mass of the entire supplement. So we're still going to use the same equation, and I'm going to say that the percentage that I have is going to be right here, the 22% for K. So I'm going to say I have 22% of the K, and because I'm looking for a molar mass, I don't want to use grams for this equation. I'm going to use the molar mass. So I need the molar mass of this right here, and this right here is the potassium. So I want to put the molar mass of potassium up top, which is going to be 39, and then I'm going to divide that by the molar mass of the entire supplement, and I don't know what that is, so I'm just going to put the molar mass here, and then I multiply that by 100, and I'll solve this for the molar mass. And when I solve this for molar mass, I get that the molar mass is going to be equal to 177 grams per mole. And so this would be the answer to part 2.